Welcome to This Explainer. Today, we're basically playing mathematical detectives to decode the hidden clues locked inside rational functions. Think about it. Have you ever looked at a graph that's just curving wildly, shooting off into infinity, or mysteriously vanishing at a single random point, and thought, how on earth does an equation tell a line to do that? Well, you're in exactly the right place. We are going to break down the sheer DNA of these fascinating equations and learn how to read their secrets. So here is our game plan for today's investigation. 1. We'll formally meet the irrational function. 2. Finding domains and intercepts. 3. The classic showdown holes versus vertical asymptotes. 4. Horizontal and slant asymptotes. 5. The 7 steps to graphing. And finally, 6. Reverse engineering the graph. Let's get right into it. Section 1. Meet the rational function. Let's introduce our primary suspect. Simply put, a rational function is really just a fraction. But instead of plain numbers, you've got algebraic equations stacked on top of each other. The top polynomial is our p of x, and the bottom is our q of x. But there's a catch, and it's a massive one. That bottom part, the denominator, it absolutely cannot equal 0. That single non-negotiable rule is the exact culprit behind all the crazy mathematical traps and wild behaviors we're about to explore. Because, as we all know, dividing by 0 basically breaks the universe. It's totally undefined. Moving to Section 2, finding domains and intercepts. We have to map out exactly where our function is allowed to exist and where it is strictly forbidden. Here is your golden rule as a math detective. Always, always determine your domain from the original, unsimplified function. Seriously, if you simplify first, you are going to miss hidden clues. You just take that original denominator, set it to 0, and solve for x. Let's say your bottom equation is x squared minus 9. You set it to 0, factor it out to x minus 3 and x plus 3, and boom, you instantly know x can never, ever be 3 or negative 3. Those numbers are permanently banned from your domain, even if things cancel out later. Section 3, holes versus vertical asymptotes. This brings us to a huge distinction, figuring out what actually physically happens on the graph at those forbidden values we just uncovered. When you factor your rational function all the way down, two things can happen to those pieces in your denominator. If a factor on the bottom perfectly matches one on the top and they cancel each other out, congrats, you've found what we call a hole, or a removable discontinuity. It's really just a tiny little pothole in the mathematical road. But if a factor stubbornly refuses to cancel and stays stuck in the denominator, you've just discovered an invisible, impenetrable brick wall, a vertical asymptote. And to be absolutely clear about what that brick wall actually is, vertical asymptotes are strict force fields. As your graph creeps closer and closer to this excluded x value from either side, the function starts to panic. It's going to shoot straight up to positive infinity or plunge way down to negative infinity. But it can never, ever cross that vertical line because the function flat out does not exist there. All right, Section 4, horizontal and slant asymptotes. Now we're looking at a completely different kind of boundary. While vertical asymptotes tell us about strict domain rules, these new ones tell us about end behavior. Comparing the highest exponent, the degree, of the top to the bottom is basically your ultimate cheat sheet for this end behavior. It instantly cracks the code of where the graph is heading horizontally. Let's call the top degree n and the bottom degree m. If the bottom is mathematically heavier, meaning n is less than m, your graph flattens right out at the x-axis, so y equals 0. If they're in a dead tie, n equals m, your horizontal asymptote is just the ratio of their leading coefficients. And if the top is heavier by exactly 1 degree, the graph doesn't flatten horizontally at all. It goes diagonal, giving you a slant asymptote, which you can easily track down using some polynomial division. Now listen to this because it's vital. These horizontal and slant lines are fundamentally different from the vertical ones. They are really just suggestions for how the graph acts way out at the extreme left and right edges. Which means our function can absolutely crash right through a horizontal or slant asymptote right in the middle of the graph. It's a guiding line for infinity, not a force field for the center of your grid. Section 5, the 7 steps to graphing. Let's take everything we've gathered and actually map out this mathematical crime scene. We've got a super solid 7-step process to get it done. We're going to build the scaffolding step by step. And notice how these first 4 steps are entirely about extracting clues directly from the algebra before you even look at a piece of graph paper. Step 1 is always factor completely. Once you cancel common factors, boom, you immediately get step 2, identifying your holes. For step 3, you just take whatever is left in the numerator, set it to 0, and you've found your x-intercepts. And for step 4, whatever survived in the denominator becomes your vertical asymptotes. Next, we bring it to the canvas. Step 5. Check the degrees of your original top and bottom to find your horizontal or slant asymptotes. This sets up the extreme edges of your drawing. For step 6, remember that your vertical walls chop the graph into distinct sections, so just plug in a few random x values in each section to see if your curve is hovering above or below the axis. Finally, step 7, sketch it. Connect your intercepts and points, hug those asymptotes, and remember, never ever cross your vertical force fields. Okay, pulling this off is incredibly satisfying, but it raises a really fun question for us. Can we run this exact same sequence in reverse? Like if someone hands us a completely blank equation, but a fully drawn graph, can we uncover the original algebra? That brings us to section 6, reverse engineering the graph. Let's dive in and see how we can build a rational function from scratch, using nothing but visual evidence. It's honestly beautifully logical. We literally just flip the rules we just learned. By seeing exactly where the graph crosses the x-axis, we construct the factors for our numerator. By spotting those vertical force fields, the x values tell us exactly what to drop into our denominator. And if we see a little open circle, a hole, at a specific x value, we know we have to place that corresponding factor in both the top and the bottom because it had to cancel out. You can even look closely at how the graph interacts with the x-axis. If it slices straight through an intercept, that factor gets a power of 1. If it bounces off the axis, it gets an even power, like 2. But wait, there's one final trick. Once you've stacked your intercepts and asymptotes into a fraction, the equation isn't quite finished. There might be a hidden stretch or compression factor at play. We usually call this constant multiplier a, and it sits right at the very front of your equation. To find its exact value, just grab one super clear coordinate point from your visual graph, any x and y that isn't an intercept or a hole. Plug those numbers into your shiny new equation and solve for a. Now your equation is a perfect match. As we wrap up this explainer, let's lock in the crucial analytical tools you've mastered today. The denominator is basically a strict boss. Its zeros dictate entirely where the function cannot exist. When you simplify, whatever cancels is just a hole, but whatever stays behind is a massive vertical wall. And the ultimate golden rule, always factor first. Seriously, if you try to analyze these things without factoring, you are flying totally blind. You now have the specialized tools to read the hidden story behind these winding, infinite curves. You've seen exactly how rules govern the chaos, dictating every single jump, slant, and hole. Which leaves us with this final thought. If you can look at a wild, looping rational graph and confidently reverse engineer the precise mathematical DNA that created it, what other incredibly complex systems out there are just waiting for you to decode them? Keep investigating, and I'll see you in the next explainer.